For decades, a shadow has loomed over our understanding of the sun, a stubborn paradox, a ghost in the machinery of our most sophisticated models that no physicist could explain. Our telescopes, eyes trained on the infernal core of our star, observed a phenomenon as beautiful as it was disconcerting: coronal shower. After a flare, a violent release of magnetic energy, we saw the incandescent plasma of the solar corona, the outermost layer, cool and fall back toward the surface in dancing filaments. But it did so with a speed that defied logic, a speed that, according to our physical laws, should have been simply impossible, a true crime against thermodynamics. The theoretical models, based on decades of established physics, were clear and inflexible. A plasma at over 1,000,000 degrees Celsius should take hours, if not days, to radiate its immense thermal energy. Yet the data didn't lie. Advanced instruments like the Solar Dynamics Observatory, or SDO, recorded a completely different, almost science fiction-like story. The condensation of the plasma and its subsequent collapse occurred in a matter of minutes. Theory and observation were at war, and no one knew who was right. This discrepancy wasn't a detail for nitpicking academics. It represented a deep and troubling flaw in the very foundations of our understanding of solar energy. If we were wrong about this, what else were we doing wrong? But now, a groundbreaking new investigation has finally pierced the veil of ignorance, illuminating the darkness with a blinding revelation. The culprit has been identified. A missing piece. Literally. The answer wasn't hidden in the complex equations of thermodynamics or plasma physics. It had always been there, hidden in the secret and astonishingly changing chemistry of our star. Two researchers, Luke Bonowitz and Jeffrey Reap, committed an act of scientific heresy. They dared to question a dogma, a fundamental assumption of solar modeling that had been taken for granted for generations. This dogma held that the corona's chemical composition, its mix of elements, remained essentially constant, an unchanging stage on which the drama of flares played out. Their computer simulations, among the most complex ever performed, revealed a shocking truth. That assumption, that comfortable certainty, was completely and utterly wrong. They discovered that during flares, heavy elements, particularly iron, aren't passive spectators. Instead, they're captured and violently dragged upward by the superheated plasma flows. This process, known as chromospheric evaporation, acts as an express elevator for heavy elements, carrying them from the solar lower atmosphere up to the extremely thin corona. As a result, the local iron concentration in the flare region undergoes a dramatic and temporary surge, enriching the plasma in ways we had never considered. And this, my friends, is the heart of the mystery. Iron and other elements with a low first ionization potential, known as low Phi elements, are tremendous energy sinks. They act like giant heat sinks at the atomic level. As their abundance in the plasma increases, the efficiency with which that plasma can release its heat does not increase linearly. It explodes exponentially. The energy is radiated away into space at a dizzying rate, triggering a cascade of cooling, a chain reaction that leads to the near instantaneous condensation of the plasma. When Bonowitz and Reap incorporated this dynamic chemical abundance into their models, magic happened. The eureka moment of modern solar physics. The simulated cooling times, which had been stubbornly incorrect for years, now matched decades of real observations with millimeter precision. The paradox was resolved. The mystery of the speed of solar rain was no longer a matter of unknown physics, but a direct and logical consequence of a continuously, violently changing chemistry. This isn't just a model fix. It's a paradigm shift, a reimagining of how we conceive and simulate the physics of flares, the engines of space weather, and the implications of this discovery are immense, extending far beyond simply understanding a fiery rain on a distant star. The point is that if our understanding of cooling was so fundamentally flawed, then our interpretation of its opposite process, coronal heating, was almost certainly also distorted. We can't directly observe how energy is released in the corona. Cooling is our only indirect window into that process. Now that window has suddenly become much clearer and cleaner. To unlock the even deeper secrets this discovery promises, and to understand how it changes everything, be sure to join us on this exploration. Stellar physics will never be the same again. The new model emerging from this research finally unifies three long-known but never-before-seen physical concepts into a single powerful and coherent mechanism. The first is the so-called FIP effect. Physicists already knew that elements like iron are naturally more abundant in the corona than in the lower solar layers, but they hadn't fully understood the dynamical consequences. The second is flare-driven flows. It was known that eruptions erupted plasma, but the idea that this plasma was chemically diverse and enriched in real time is the real novelty. The third is uncontrolled condensation. The high local concentration of iron creates cold spots that trigger a gravitational collapse of the plasma, which falls as rain. Old models, with their fixed abundances, completely ignored this leading actor, flattening a complex three-dimensional reality into an imprecise two-dimensional simulation. The new dynamical approach not only explains the phenomenon's rapidity, but also its morphology. It explains why coronal rain appears in filaments and complex structures following iron-enriched magnetic field lines. This means that the radiative loss functions, the equations that are the heart of almost all existing coronal models, urgently need to be rewritten from scratch. They must now incorporate a chemical composition that evolves over time and space, a computationally Herculean task, but no longer optional. It's a necessity, and the impact of this discovery is spreading like a shock wave through astrophysics. It doesn't stop at the edges of our solar system. Billions of other active stars in our galaxy, red dwarfs for example, exhibit even more violent flares and coronal showers than ours. If the dynamic chemistry of iron is the key to understanding our Sun, then it is almost certainly the Rosetta Stone for deciphering the activity of countless other worlds. We are witnessing in real time an epochal strengthening of the link between chemistry and energy, a giant step toward a holistic understanding of stellar physics. The practical implications of all this are immense and will have a direct impact on our life on Earth, starting with our increasingly critical space weather. More accurate and faster modeling of flare cooling translates directly into much more reliable predictions of the evolution of coronal mass ejections, CMEs. These immense bubbles of plasma and radiation blasted from the Sun are the primary threat to our technological civilization. Better forecasts mean real protection. Communications satellites, GPS systems, civil aviation, and even national power grids are all vulnerable to the devastating effects of a direct solar storm. This seemingly esoteric discovery may one day be the reason our lights stay on during the next inevitable solar big one. Additionally, spectral diagnostics, the way we analyze sunlight to understand its composition, will become much more precise. Updating instruments to account for real-time variations will make solar mission data much more accurate, and future space missions are already poised to test this new theory. They were designed almost presciently for this task. Revolutionary probes like ESA's Solar Orbiter and NASA's Parker Solar Probe are flying closer to the Sun than ever before. They can taste the plasma and measure these chemical changes in real time, right as they happen. We are entering an exciting new era in solar physics, where chemistry is no longer considered a background detail, a boring constant in models. It has become what it has always been, a leading player, a dynamic and powerful agent of chaos, shaping our star's environment and, by extension, our own. The lesson is profound. Even an object we've studied for centuries, like the Sun, can hide fundamental secrets in plain sight, waiting for the right question and the courage to challenge dogma. What does this tell us about our ability to truly understand the universe? And what other, even greater secrets lie hidden behind the veil of our current certainties, poised to once again overturn everything we think we know?